Have you ever wondered why a stable salt, such as cobalt trichloride, combines with a group of stable, independently existing molecules, such as ammonia, to form new compounds like COCl3, 6NH3, COCl3, 5NH3, and COCl3, 4NH3 with entirely new properties? Alfred Werner, a Swiss chemist, after preparing thousands of new compounds and studying their properties, put forward a theory to explain the formation of complex compounds. It was the first successful explanation for the phenomenon. The theory became famous as the coordination theory of complex compounds, which is also known as Werner's theory. His explanation of complex formation is based on some postulates. The first postulate is that the central metal atom or ion in a coordination compound exhibits two types of valencies, primary and secondary. While writing the structure of the metal complexes, the ligands that are linked by primary valency are shown by dotted lines, while those linked by a secondary valency are shown by thick lines. If a ligand satisfies both the valencies, then it is shown by a thick as well as by a dotted line, and it is said to exhibit dual character. The second postulate is that primary valencies are ionizable and correspond to the number of charges on the complex ion. Primary valencies apply equally well to simple salts and to complexes, and are satisfied by negative ions. For example, the primary valency of 2 in COCl2 is satisfied by 2 chloride ions. Similarly, the primary valency of 3 in the complex CONH36Cl3 is satisfied by 3 chloride ions. In modern terminology, the primary valency corresponds to the oxidation number. The third postulate is that secondary valencies correspond to the valencies that a metal atom or ion exercises towards neutral molecules or negative ions in the formation of its complex ions. Every metal has a fixed number of secondary valencies or coordination number. For example, cobalt 3+, platinum 4+, and iron 3+ ions are recognized to have a coordination number of 6. Similarly, nickel 2+, copper 2+, and platinum 2+ ions have a coordination number of 4. Secondary valencies are non-ionizable. They are satisfied by neutral molecules or negative ions. The secondary valency is equal to the coordination number of the metal. For example, in the complex COCl3, 6NH3, the 3 chlorides are held by primary valencies and the 6 ammonia ligands are held by secondary valencies. The fourth postulate is that secondary valencies are directional, and so a complex has a particular shape. The number and arrangement of ligands in space determines the stereochemistry of a complex. The most common coordination number in transition metal complexes is 6, and the shape is usually octahedral. The coordination number 4 is also common, and this gives rise to either tetrahedral or square planar complexes. This postulate predicted the existence of isomerism in coordination compounds. To distinguish between the two types of valencies, Werner introduced the concept of using square brackets to enclose the atoms that make up a coordination complex and which are, therefore, not ionized. The postulates of Werner's coordination theory were actually based on experimental evidence rather than theoretical. Werner treated cold solutions of a series of compounds of cobalt 3 chloride with ammonia with an excess of silver nitrate and weighed the silver chloride precipitated. The stoichiometries of the complex silver chloride formed were as shown here. Werner deduced that in COCl3 6NH3, the primary valency or oxidation state of +3 is satisfied by 3 chloride ions. The coordination number of the cobalt 3+ ion is 6. As there are 6 ammonia molecules in the compound, they alone satisfy the 6 secondary valencies of cobalt. As you can see, the primary valencies are represented by dotted lines and the secondary valencies by thick lines. In modern terms, the complex is written as CONH3 6Cl3. The 3 chloride ions are ionic and hence are precipitated as silver chloride by silver nitrate. Thus, the complex will ionize in solution and give 4 ions. That is, 1 CONH36 3+ ion and 3 chloride ions. Werner deduced that the loss of 1 ammonia molecule from COCl3 6NH3 should give COCl3 5NH3. This complex has only 5 ammonia molecules. Therefore, to satisfy the coordination number of 6 of cobalt, 1 chloride ion assumes dual behavior. That is, it satisfies the primary as well as the secondary valency of cobalt. In modern terms, the complex can be written as CONH3 5Cl Cl2. Thus, only 2 of the 3 chloride ions are ionic, and thus only 2 are precipitated as silver chloride with silver nitrate. On ionization, this complex will give 3 ions. 1 CONH3 5Cl 2+ ion and 2 chloride ions. As can be seen from its structure, one chloride ion, which is playing a dual role, is shown by a thick as well as a dotted line. Similarly, in COCl3, 4NH3, to satisfy the secondary valency of 6, two chloride ions assume dual behavior. In modern terms, the complex can be written as CONH3 4Cl2Cl. Thus, only one chloride ion can be precipitated as silver chloride. This complex, on ionization, gives two ions, one of CONH3 4Cl2 plus and the other of chloride ion. The structure of the complex is shown here. Although Werner's theory successfully explains the bonding features in coordination compounds, it suffers from some drawbacks. It doesn't explain why only certain elements form coordination compounds. It does not explain why the bonds in coordination compounds have directional properties. It does not explain the color and the magnetic and optical properties of complexes.